Hello class, welcome to this video on lesson 4.3 to two-way tables and Venn diagrams. So our goals for today are to be able to use two-way tables to find probabilities, calculate probabilities with the general addition rule, and use a Venn diagram to find probabilities. So we want to address the question, how do we calculate probabilities using these tools, the Venn diagram, two-way table, or just by using an addition rule known as the general addition rule. So first off, let's take care of a few vocab terms, such as what it means to be mutually exclusive. So in general, you're going to have to calculate the probability of events happening, and some of the events may be mutually exclusive. And this means that these are events that can't both happen at the same time, so they can't happen simultaneously. So you may So essentially what you have is two events, or you have event A or event B. Now, sometimes we use the word or, right? Which means exclusive or, meaning it's only, you only have to, you can only make one option, right? You choose A or you choose B. Now, sometimes we use the word or to mean choose A or B or both, right? So if someone asks, do you want sugar or cream on your coffee? You could say both in that case. And in that case, that would not be mutually exclusive. But they could ask another question in which you have to choose one option, and that would be mutually exclusive. Okay, so events that cannot both happen at the same time. All right, so some examples of this are, for instance, a coin toss, right? So in this case, in the event of a coin toss, heads and tails are mutually exclusive, right? So getting heads and tails are mutually exclusive events. And this is for a single coin toss, so I should probably mention that. We got a single coin toss. Heads and tails can't happen at the same time, right? Another example, so I'll list one example here. I'll list another one, is in a standard deck. So like a deck of playing cards, right? Drawing a single card. So I'm going to put this in parentheses. If you were to draw a single card, and you get kings and aces, right? That can't happen at the same time. Getting kings and getting aces cannot happen if you're drawing a single card, right? So I'm going to say getting kings and aces. Okay. All right. So that's what it means to be mutually exclusive. There's no overlap. Cannot happen at the same time. In a Venn diagram, we show we show mutually exclusive events as events that do not overlap. Right. So a Venn diagram consists of one or more circles, and usually you have a rectangle around it. Now the circle represents the event, right? So a particular event, and then the region inside the rectangle is the sample space. Okay, so everything inside the rectangle represents the sample space, and if you recall, the sample space is the set of all outcomes that can happen, right, in that particular environment, or experiment. So in this case, we have non-mutually exclusive and mutually exclusive. So notice that mutually exclusive, the events cannot happen at the same time, and therefore they are disjoint, right? So notice that they're separated from each other. There is no overlap, right? And then non-mutually exclusive, that may not be the same thing. You could ask for both coffee and sugar, for instance, and that would be in the middle, right? Okay, so union. There are a couple operations that you need to know how they work in probability and in set theory as well, and a lot of things. But in terms of probability, the union, the symbol that we use is sort of like a capital U. So that's known as union, and the definition is in the event A or B. So sometimes we just refer to it as or, which is the union of the two events. Consists of all outcomes that are in event A or in event B. Or both. Okay, so the union or the use of or in union actually includes is the idea of, so I'm gonna put this example, right? Sugar or cream in coffee, for instance, meaning you could have one or the other or both, right? Potentially. So that think of that as union, right? Intersection. So the symbol is the upside down version, right? Right here, it's easy to remember that way. And this refers to the event A and B. So that means that it's all the outcomes that are in both, right? So it has to be in both. So an event A and an event B, or all outcomes that they have in common. Okay, so let's go ahead and recap those symbols. So we have, if you have A or B, then that's A union B. And then here we have A and B, it's A intersect B, okay? And if the events, well, let's go ahead and take a look at this. So down below, we have it set up so that one row of Venn diagrams is non-mutually exclusive, and then the other row is mutually exclusive, right? So if we had non-mutually exclusive events, meaning they have some overlap, that means that when you're trying to do the OR operation, you're going to be including everything in either in both A and or B, right? So you're going to be shading everything. Now, if you're doing A and B, you're only going to shade what they have in common, you see, which is this guy. In the case of mutually exclusive events, there is no nothing in common, so there's nothing to shade. Okay, so that's how we're going to do it. We're going to be shading whatever parts are relevant. Okay, so we're going to go over several scenarios here, and what I'm gonna do is I'm going to shade several scenarios for several Venn diagrams. Okay, so there should have been an A and a B here. So let's go ahead and shade what happens in a Venn diagram if you are only trying to shade, or you're interested in the outcomes of A only. Okay, so for example, the probability of A, right? So what happens? So in this case, if you're just focusing on A, then obviously you're just going to shade everything in A. Okay. And that may include some stuff in B, right? Because they overlap, and therefore if you're trying to do A, you're going to end up doing some in B, but that's okay. When you're doing the probability of A, for instance, you're including everything in A, so you would have to shade everything in A. Okay. Same thing here. If you're including everything in B, then you must include that part, right? All right, now they're mutually exclusive, so you only have to shade parts of in A, right? There is no overlap with B. And in this one, there is no overlap with A. All right, so those are a couple scenarios. Let's go over a couple more scenarios. Now, I forgot to mention that there's another operation here, which is known as the complement, right? So I'll put that over here because I forgot to include that in the notes here. Okay, and the reason why I didn't include it is because the reason I didn't include the definitions because we did it in the previous video, but I do want to refresh your memory here again. So the complement of an event is essentially anything that is not. So we usually say the event not A, for instance, if you're doing the complement of A. It's basically the set of all outcomes So the set of all outcomes not in, for example, event A. Not in the event. I'm just going to say not in the event. Okay. So in this case, we usually refer to as AC, A complement, or A prime, right? So either way, you're gonna see this A prime here, this little prime symbol, and that just means complement. So anything that is not in A, so that means you have to shade everything that is not in A, which would mean B, but it also means everything that is in this, everything else in the sample space that is not in A. So that means this rectangle as well, right? That's everything that is not in A. Okay, and then similarly here, anything B complement, anything that is not in B. So that means you can't shade where they overlap because that's in B. And then everything else outside. Okay. And then here we have a complement. If they're mutually exclusive, then you're just shading everything in B this time. Whereas here you didn't shade everything in B, right? You're not including everything in B because some of it overlaps, as well as the outside portion. Here, you're including everything in A and everything outside here. All right, so hopefully that makes sense. Here's another operation that we mentioned, the union and the intersect. So again, as we mentioned earlier, union, you're going to include all outcomes when you calculate probabilities, include all outcomes that in A or B or both. So there you go. And then intersect, only include what's in A and in B, meaning where they overlap. Now here there's nothing to shade for because they are disjoint, right? So in this case, A intersect B is empty, and this is known as the empty set, right? It's a set of nothing. There's no elements in that set, so there's nothing to include or to shade here, right, for the probability. So in this case, the probability that this happens is going to be 0, right? So the probability of A intersect B in this case is 0, whereas in this case it's non-zero, right? So in fact, this is how you can determine if the two events are mutually exclusive or not. If the intersect, the probability of the section of the events is 0, then we know it's mutually exclusive. So in fact, we can include that in the definition in your notes whenever you get a chance. Okay. All right. So A union B, we have everything in A, everything in B, or both. But there's no nothing that they have in common. So you're just shading A and then the B circles. Now here we have A and B complement. So first off, I'm going to shade them separately, and then we know that B complement is, and I'm going to shade them in different colors, right? Because that's going to help. So B complement is everything that is not in B. So let's focus on A first. So let's do A blue, A in red and B in blue. So A is everything in A, and B is, and I wouldn't shade anything just yet because we're going to give you the final answer. And B complement is everything that is not in B, right? So that means not in B. So that means you can't shade where they overlap. You can shade that, and then you can shade everything not in B, which is on the outside. So notice intersect means what they have in common. Well, what do they have in common? Well, they have this portion in common, right? So that's the part that we're going to shade. So therefore, I'm going to shade all of that. And blue and red will make purple, so I will just shade that part. And then we can get rid of everything else. Okay? So that's the part that you would include. So if they're disjoint, right? Then if you're to do the same thing, anything that is in A, anything that is not in B, Everything that they have in common is here. So you would just strictly shade A. Okay, all of A. All right, and then here you have A union B, the complement of A union B. So first off, you need to do A union B. So A union B is so A or B or both, right? So that's A union B, and then the complement of that. So the complement of that is everything that is not in that, which means anything on the outside, right? So then you're going to just shade everything that's on the outside. And then you're going to exclude that part, right? Because you're doing anything that is not the original, okay? So the answer is you're going to shade everything on the outside because it cannot be in the inside because we're doing the complement. All right, and then same thing here, A or B. However, we don't want A or B. We want the complement, right? Which is everything else. So we want everything else. So we're again, same deal. We shade everything on the outside. All right, so those are some scenarios. There are tons of scenarios out there for the different operations, but I wanted to give you a few. And that's how you would set up and shade the Venn diagrams. Now we're going to actually give an example of this, but before we do that, first we need to go over real quick how we calculate the probability. So and just to kind of recap, the way to calculate the probability is, remember the denominator is all the outcomes in the sample space. So the all outcomes in the sample space. And the numerator are all outcomes in the event, right? The event of interest. So outcomes, number of outcomes in the event, okay? So you're gonna have the probability of an event is the outcomes in the event, you know, that you're interested in the event of interest, and then out of all the outcomes in the sample space. I guess I should say all possible outcomes, right? All possible outcomes. And that's how you generally calculate the probability. So for here, example 1, we're going to set up a Venn diagram for the given scenario, and then we're going to figure out what to shade, and then we're going to calculate the probability. So there are 51 students in biology and 24 students in chemistry. There are 7 students taking both classes, and there are 90 students in total. So let's set up a Venn diagram first, and then we can calculate the probabilities. Okay, so first off, you have, we're going to say that, and we're looking for B and C. Notice that there's B and C. So we're going to say this event B are students taking biology. Student is in biology. And event C, student is in chemistry. So in this case, okay, so let's go and set that up then. We have our B and our C. Are these mutually exclusive events? Well, in this case, the answer is no, they're not mutually exclusive because we have 7 students that are taking both classes, right? So in this case, in general, these are not mutually exclusive events. You could take potentially, and according to this scenario, both classes. So we're going to say that in this case, it's going to be both. So in this particular scenario, we could potentially take both. So in this case, what we're going to do is we're going to do biology, chemistry. They are joined. And then there's the sample space. So 7 students it says 7 students in both. So let's put a 7 in there, and that represents the number of students in both. And then there are 51 in biology, which means that if we do 51 take away 7, that's 44. And that gives you the number of students that are just in biology, right? But not in chemistry. These 7 students are in biology, but they're also in chemistry for a total of 51, right? And now for chemistry, there are 24 students in chemistry. However, 7 of them are also in bio. So we're going to take the difference and get the students that are just in chemistry, which is 17 students. Now, there are potentially students that are not taking either, right? Either of the classes. So we're going to, but we know there are 90 students in total. So we're going to figure out how many are not taking either class, right? So 90 take away, and then we're going to add up these numbers here. So we know this is 40, 44 and 7, that's 51. 51, so let me just take the sum of these numbers. Okay, so 90 minus 44 plus 7. So if I add these, right, that's 51 plus 17. That's 68. So it's 90 minus 68, which is, in this case, 22. If I did that math correct. Yeah. All right, so we got 22 students that are in neither. So I'm going to put that over here, 22. So they're on the outside. And these are neither course. All right, excellent. So now we can go ahead and calculate the probabilities. So again, so probability that a student is in biology. So if we're doing the probability that a student is in biology, we are going to be shading everything in the bio circle, which is 51 students, right? That includes the 7 that are in chemistry, because it doesn't say anything about excluding those students. So it's going to be 51 students in biology over the sample space, which is everyone, right? Which is everyone. So that's the 22 people here and all these people. So it's 90 students, right? And that's our probability. And of course we can compute that as a decimal. So let's actually do that. So we got 0.5. And then we'll round. So let's see. We'll round to 3 decimals, 0.567. All right. So now let's do probability that a student is in biology and chemistry, which means that's the 7 that are in both, right? So it's 7 out of 90. Again, we could have computed this without using the Venn diagram, but again, I wanted to show you how you would be able to set it up. We'll round that to 0.078. And then we have C and B complement. C and B complement. Okay, so remember C and B. So C is everything in C. And then B complement is everything that is not in B, which includes this and includes the outside. But what do they have in common? They have the 7 in common, right? Oh no, not the 7 in common, I'm sorry. They have the 17 in common, right? So they have this part in common. So therefore we're looking at the 17 portion, okay? So in this case, we have 17 over 90. So these are, if you were to kind of write this in English, so just in words, right, rather than with the symbols, you would say, you know, what's the probability that a student is in chemistry? Well, you would say is in chemistry, and they're not taking biology, right? So a student is in chemistry and they're not taking biology. So then that means you would exclude the students that are taking chemistry and bio at the same time. So you would exclude these guys. So you're just looking at the 17. So that makes sense. All right. And then we have, finally, we have what's the probability of selecting a student that is taking biology or chemistry? Okay, so biology or chemistry, that means you would shade everything, biology or chemistry or both, right? So you would do, you would add these numbers. So 44 plus 7 plus 17. So that's 51 plus 17 is 68. So you would have 68 over 90. And we will figure out what that is. And we can reduce that. So we're going to reduce that here. So we can reduce that to 34 over 45. And that's going to be 0.756. All right. So that's how you calculate the probabilities for various events. So notice that when we calculated the union, right, we added these numbers up, right? But notice if you look at the problem, they said that there was 51 in biology and it's 24 in chemistry. So if we just added those numbers, 51 plus 24, we're actually going to get more than we were supposed to, right? We're going to get 65. And the reason why we get more when we add the numbers that they gave us here, biology or chemistry, is because we have to exclude those students that are taking both, right? So whenever you're trying to calculate a probability of some sort, right, or the number of students, you have to take into account that there may be people that are doing both events or both classes in this case, and so you got to exclude them. Otherwise, you're going to count them twice, right? So this is why we have to. I said I said 65. Let's just say 75, right? 75 is greater than what we had here, 68. So we had to take away the 7 students that we counted twice. So that's known as the general addition rule. So in general, in order to add combine the outcomes of 2 events, you have to take away what they have in common if they're not mutually exclusive, okay? So the general addition rule states that if you're doing the union of 2 events, A union B, or A or B, right? You're going to add the probability of A and add the probability of event B occurring. So you're going to combine the 2, but then you have to make sure to take away anything that they have in common. Okay. So, for instance, in this example that we just did, B union C, we would do probability of B plus probability of C minus the probability that both events can occur. So the probability of B, which is the biology, we calculated here is 51 out of 90, right? So 51 out of 90. And then the probability of chemistry, well, how many students are taking chemistry? Well, it's 24 students, right? So 24 students. So you would say 24 out of 90. But it's not enough to just combine them because there's students that are taking both. So you got to make sure that you don't count them twice and you take away any that are doing both, which is 7 out of 90. And if you do this, you're going to get the answer that we had earlier, which is, what was it, 68. Yeah, 68 out of 90. Okay, so let's take a look at another example. So example 2, a 2014 survey suggests that 71% of US teenagers use Facebook, 33% use Twitter, and 15% do both. Suppose we select a US teenager at random. What's the probability that the student uses Facebook or uses Twitter? So let's go ahead and denote the event F as a teen uses Facebook. So we select the teen that uses Facebook. And we'll denote T as the event in which we select a teen that uses Twitter. And so we're selecting someone at random. What's the probability that the student uses Facebook or, so that's a conjunction. I will also mention real quick that sometimes we refer to, if we go back here, sometimes we refer to union. We refer to union as disjunction. And we refer to intersection as conjunction. So sometimes we could refer to as A or B as A, disjoin B, the disjunction of A and B. Or you can say, if you're doing A and B, A conjoin B, like A and B, the conjunction of the two. So sometimes you'll see me refer to that. So here we're doing the disjunction of the two. So we're doing a disjunction or the union. All right, so we're going to take, according to the general addition rule, it's the probability, so I put A and B, A or B, sorry, I should have put F or T, so Facebook or Twitter. It's the probability of a teen selecting Facebook plus the probability of a teen selecting Twitter minus the probability that a teen selects both, uses both platforms. All right, so in this case, we have 71%, which is 0.71, use Facebook right here. And then 33% use Twitter. But notice if we add these together, we get over 100%, right? We get 104%. And that's because we forgot to exclude those that do both, because we're counting them twice, right? We're counting them for the Facebook and we're counting them for the Twitter as well, because they belong to both groups. So we're going to take them away. So 0.15, and then it should go back to where it should be. All right, so we got 0.71 plus 0.33, which we said was 104%, 1.04. But then we take away the 0.15, okay? And that will give us our probability. So in this case, it's going to be 0.89. For our probability. Okay. All right, so let's take a look at another example, final example. Students in a college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether or not the student had a pierced ear, for all 178 people in the class, and we have the two-way table. So we're going to actually use a two-way table. We mentioned what a two-way table was because we used it in a previous lesson, in a previous chapter, right? So now we're just using the two-way table just to do the probability instead, okay? So we used a two-way table for categorical data, if you recall, in order to, make graphs with categorical data. So suppose we choose a student from the class at random. Define event A as getting a male student and event B as getting a student with a pierced ear. Find the probability of B, so which is a student getting a student with a pierced ear. Okay, so probability of B. So the probability, so we'll do that as part A. So the probability that you select student with a pierced ear, so that means you're going to say yes to the pierced ear. So you're looking at this row, right? So the probability of selecting a student with a pierced ear, well, there's 103 students or young adults that have their ears pierced in this sample, right? So 103 out of the total, right? The sample space, the total. In this case, in this case, the sample space is like all the people that you've collected. So this is a theoretical or based off of data, an empirical probability. So we have our 178. Okay, so again, to calculate this probability, we take in this case the number in the event over the total. Okay, that's how we'll be able to calculate this. All right, so we got 103 pierced ears, young adults with pierced ears, over 178 in our total sample, and then that's our probability. Go ahead and compute that as a decimal. So that's 0.579. Again, we're going to round to 3 decimals there. All right, and then the probability of male. So male student is event A and pierced ear, right? So and B. So male and pierced ear. So yes to pierced ear. So we're looking at this row. But we're looking at male. They have to be male. right? So if I were to do a Venn diagram, it would be one circle would be pure steer. One circle would be male. What do they have in common? Well, they have the 19 in common, so male and pure steer. So we're looking at 19 that satisfy that out of the total of 178. Okay, so this is 19 out of 178. So we got 0.107 or 10.7%. And then finally, we have the disjunction of A and B. So A or B. So we got A was male, so male or pure steer, male or pure steer. So we got male, everything in that, or everything in here, right? Okay, so essentially what we're going to do is we're just going to use a formula. This is the general addition rule. So the probability of male plus the probability of pierced ear minus the probability of both. That way we don't count it twice. So what's the probability of male? Well, there's 90 males out of 178, right? So 90 out of 178. So when you do these kind of probabilities, it's best just, it's, you know, safe to just use the rule. And then the probability of a pierced ear, well then the total for pierced ear was 103 out of 178 minus, and then you're going to take away the male and the pierced ear, which was the 19 that we got earlier in part B. Okay, so we're going to go ahead and combine those to get 174 out of 178, and which is 0.978. Okay. All right. So we got roughly 98% in either category, which means if they said those that don't have those characteristics, so not male, you know, not pierced ear, it's everything else. All right, that's going to do it for the video, guys. I hope you found this useful and informative, and as usual, I'll see you in the next one.